Okay, so we're going to be going over Note 2 from CS70. This one is going to introduce us to the concept of proofs. Okay, so what do proofs allow us to do? They allow us to rigorously determine that something is true, like guarantee that something is true. The definition of a proof, let's see, it's a finite sequence of steps that establishes the truth of a statement. So, you know, the comparison they made in Notes is that in science, we form a hypothesis and then we run experiments to gather evidence for a specific viewpoint, but in terms of math, in terms of actually proving something, we need something that's more concrete, that's actually absolute. And so we're going to go into some of the notation for proofs and some facts about it. So the set of integers is closed under what operations? So this is just something that we should be aware of. Addition and subtraction, you know, if we think about the set of integers, it's, you know, negative infinity and then whole numbers all the way up to positive infinity. And if we add those numbers together, we'll still get a number that's within the set. Similarly, if we multiply them, but if we were to divide the numbers, say we were going to do 3 divided by 2, that would yield 1.5, which is not in the set of natural numbers, or sorry, set of integers. All right, and what is this notation right here? Well, this plays an important role in a lot of the proofs that we are going to work out. This means A divides B, and specifically it means A divides B evenly. Another way of thinking about this is saying that B is equal to A times some multiple, something like this. Okay, and we're going to give if we want to set some variable equal to something in proofs, we say variable x colon equals and then whatever quantity we want to assign to it. So, you know, looks like that. Okay. Now we're going to go on to the first actual method of proving something, and this is called direct proof. And all of these theorems are going to be proofs that we are going to write out in Paint. And the first one says that for any a, b, c in Z, if a divides b and a divides c, then a divides b plus c. Okay, so how do we prove this? Well, I'm going to switch over to Notes so we can go over it really quickly. So, yeah. So we're saying, let me get this plugged in. Yes, it's plugged in. So I'm actually not going to prove that because this one, the proof of that is in the notes. What I am going to prove is the next statement, and I'm really just moving on for the sake of time. So this statement is actually, you use the same set of steps to prove it, so I'm just going to use it really quick. So for any of these three numbers in the set of integers, a divides b and a divides c, then a divides b minus c. Okay, so again, switching over to Paint, I'm just going to write out sorry, I don't really see it. Should be here somewhere. Give me 1 second. Okay, let's get into it. So we are saying a divides b and a divides c, then it must be the case that a divides b minus c. Now we want to figure out, is this true? Well, if we remember from before, another way to represent this is to say b is equal to a times some multiple, we'll call it x, right? Similarly, c is equal to some multiple of a, right? And we'll call that multiple y. And, you know, if we take this equation and substitute these values in for it, we get, and I'll just actually spell this out. We'll say b minus c is equal to ax minus ay, which is equal to a times x minus y, which we can tell by looking at it. We know that a clearly divides a times x minus y, because we know once this divides out, we're going to be left with this, which is in the set of integers. Okay, so hopefully that makes sense. The proof for the addition one, where a divides b plus c, is literally the same. We just honestly just change the sign, and that's it. So I'm going to erase that. I'll just make a new page. Okay, so that is a direct proof. In this case, we pretty much just used some algebraic manipulation to come to our conclusion, and some rules. The a divides b rule, for example. Okay, so that one was pretty straightforward. Let's see. The next one is let 0, so let there be an integer from 0 to 1000 in between that range. We're going to say if the sum of the digits of n is divisible by 9, then n is divisible by 9. So I'm going to actually go through this one, and then I'm going to prove the converse, which states that if n is divisible by 9, then the sum of the digits of n is divisible by 9. So let me just go through the first one. So the first thing that we can do is we're given a number n, right? And let me make sure I'm in Paint. We're given a number n, and we're going to say that its digits are a, b, and c. A, b, and c. And we know that the number is between 0 and 1000, so you know, n is not actually equal to abc. What it's equal to is 100 times a plus 10 times a, or times b, plus c. Right, so hopefully this makes sense, because each digit is in the proper place. Like c is in the ones place, b is in the tens place, a is in the hundreds place, right? And then we also say that, you know, if this is the case, if the sum of the digits of n is divisible by 9, then n is divisible by 9. So because a, b, and c are the digits, and we're saying if a plus b plus c, so if all of this is divisible by 9 plus c, then it must be true that, you know, this is also divisible by 9. Right, so let's get an equation going. We're going to say the sum of the digits. We're going to say a plus b plus c is equal to 9 times some unknown multiple. We'll just call it k. And now we're simply just going to make this side look like this, okay? And if in doing so, we generate something on this side that is divisible by 9, then we have obviously proven that this is divisible by 9. So we're just going to add, you know, what's left in order to reach this. So we're going to add a 99a and 9b to both sides, right? I'm just going to write that off to the side. 99a and a 9b. C is already there. So we are going to say, what is this? 100a plus 10b plus c is equal to 9k, and let's see, am I starting to get off screen? Almost. I'm going to squish the last part. So it's equal to 9k, plus, and what is it? We added a 99b, a 99a plus a 9b, and we can obviously tell that we can factor out a 9, and so what that would look like would simply be 9 times k plus 11b plus, not b, 11a plus b. Okay, yeah, that's just on screen. Okay, and then we can tell just by looking at it that this is divisible by 9, and so because of that we can conclude that this is divisible by 9, and we have shown that if the sum of the digits is divisible by 9, then the actual number itself is divisible by 9, right? But now we want to show the converse, which is if, and looks like I'm gonna have to make another page again. What we want to say is if it's true that if it's true that 9 divides 100a plus 10b plus c, then it must be true that a plus b plus c is divisible by 9. So we'll say 9 divides a plus b plus c. Okay, so let's see how we're going to go about doing this. We can take this and then set up just a regular equation, kind of like the way we approached this last time. So we're going to say 100a plus 10b plus c is equal to 9 times some k, right? And really what we're going to do is kind of use the same terms that we used last time to get it into a form that looks like that, right? So in this case, we can simply take out and subtract 99a and subtract 9b. Do that on both sides. And then we're going to say a plus b plus c is equal to 9k minus 99a let's see, minus 9b. In this case, we can simply take out a plus b plus c and say that that is equal to 9k minus a minus b. Okay, and as we can see, a plus b plus c is pretty clearly divisible by 9. And so we have also proved the converse. Okay, so now we're going to switch back to the notes. Okay, so right, these are the original steps that we talked about. This is from direct proof. I'm just kind of, yeah, this is the work that I did. Something we didn't go over. If we prove the converse and it turns out that if P implies Q and Q implies P, then we have proved this statement right here. Okay, and then that was for direct proof. Let's see. Now we're going to move on to the fourth section, which is proof by contraposition. So if we remember, if P implies Q, then the contraposition of that will have the exact same truth table. And the contraposition is not Q implies not P. Because it's like contra. I mean, this is how I think of it. Contra. We switch the hypothesis and the conclusion, and it's contraposition. Or I guess position is the one that switches, and then contra is the one that switches the signs. You can think of it however you want. But we're going to use that to prove theorem 2.4, which says that if there is a positive integer n that is divisible by d, then if n is odd, then d is odd. So I'm going to switch over to Paint to work on this one. So we're just going to kind of make a note. I'm not really going to do this super formally for the actual proposition. If d divides n, well, so this is kind of given, that d divides n, but we're going to say specifically what they ask from us is if n is odd, then d is odd. So something like, if n is odd, then d is odd. And it turns out it's actually easier to prove the contraposition, which is basically if d is even, then it's the case that n is even. Okay, so yeah, turns out that this is easier to prove. So let's get into the proof. Just give me 1 second. I want to look at. So we are assuming that d is even, right? So that means that d is divisible by 2. Okay, and d is in the same set as n, which is positive integers. Okay, so again, because d is even, we can say this. We can also express that as some multiple, just call it x. Okay, and then we know that d divides n, right? So we say d divides n, and d can be represented as 2x, right? So if we say, you know, down here that what is it? N is equal to d times some multiple y. We know d is 2x, so we can say n is equal to 2xy, and this is pretty clearly evidence that n is actually divisible by 2, because we can rewrite this as what is it? We can easily just make this its own variable. We can call it z, and we can say 2 divides n like that. Okay, so see, proving the contraposition made this a lot easier. Yep, so I'm going to make a new file again. Let's save. Okay, let's prove the next theorem. This one is called the pigeonhole principle. So, and just so we can see, you know, the contrapositive, we wrote that out. We wrote the propositional logic, and yeah, this is the proof that we gave. Okay, so now we're going to go on to the pigeonhole principle, which is saying n and k are positive integers, and we're going to say if we place n objects into k boxes, if it's the case that there are more objects than boxes, then at least one box must have multiple objects in it. I mean, and that pretty clearly makes sense. If you have 3 buckets and 5 balls, and you want to put all of the balls into, you know, all of the buckets, you're going to have to double up on some buckets. And it turns out if we want to prove this, we pretty much just take the contrapositive of the statement, which says, so just one bucket, multiple objects. So if all the buckets contain at most one object, then it's the case that the number of objects is less than or equal to the number of buckets. And we simply just take the contraposition. So if all the boxes have at most just one, yeah, it's pretty much what I just said. I mean, to me, the statement seems pretty self-evident on its own, and I'm not honestly too sure why this one actually proves it, because both statements seem to be pretty self-evidently true on their own. Maybe I can add that to the questions. Another question I had was on this part of the notes, and then I'm just going to add really quick how does the contrapositive of the pigeonhole principle prove it? Both statements appear to be self-evidently true. Okay, that's just a little note to myself. We're going to move on to the next section, which is proof by contradiction. And essentially what it is we're going to take our statement and we're going to take the converse of it, or we're going to assume that it's false. And we're going to try to prove the version that it's false, like the false version of it, right? And we're going to see that if we assume that the false version of our proposition is true, then it leads to something that is not possible, namely the law of excluded middle, which is we find that if we assume that this statement is true, we're going to generate a statement usually referred to as R, which is true, and then we're also going to generate another statement, not R, and that is also going to be true. But we know that by the law of excluded middle, R and not R cannot simultaneously be true. And this is essentially what we are going to do to prove that the inverse of our original claim is false, because it can't be true, essentially. So yeah, I sort of talked about that here. We're going to prove this theorem. There are infinitely many prime numbers, and this one is sort of an interesting one. It's a bit longer than the other ones, I believe. But so we're trying to say there are infinitely many prime numbers, right? But the whole issue with that is it's really hard to even go about that. How do you, using a finite sequence of steps, as per the definition of proofs, prove that something is infinite, right? How do you do that? So we're going to prove the opposite of it and show that that is false. So we're going to say that we're going to assume that there are a finite number of primes, right? So if that's the case, then the first thing we're going to do, and I believe this is the right way to go about it, is we're going to say that there is this number, we can just call it, say Q, and, oh, sorry, something I actually forgot that we're going to need is lemma 2.1, which lemmas are extremely useful. You can think of them as functions. You don't really need to know why they work, you just need to know that they will work. So you can just like plug them in to skip a whole bunch of steps that you would otherwise have to prove. And let's see, so let's use the lemma, which was what? The lemma in this note was 2.1, and it said if a number is not a prime, then it has a prime divisor, or it is divisible by a prime number. Okay, so switching over, let's see if I'm able to do this. So we're assuming that there are a finite set of prime numbers, right? So that means we could enumerate them as P1 and P2 all the way up to PK, which is the last prime number. And we're going to say there's this value Q that's going to be equal to the product of all the prime numbers plus 1. Okay? And we'll see why we have this in a bit. And this number right here, by definition, cannot be prime because it is the product of all of the prime numbers. And because it is simply larger than all the prime numbers, then it can't be a prime number itself. So Q is not prime. And as per lemma 2.1, if it's not a prime, then it has a prime divisor. Has a prime divisor. Okay? So we're going to keep this in mind. This is going to be our statement R, and we know that R, you know, we've proven that R is true, that it has to have a prime divisor as per lemma 2.1. Right? Okay? So that's cool. So next, we're going to come up with another variable. I'm sticking pretty close to the notes, actually, I think. And we're going to say that we're going to have R be equal to the product of all of the prime numbers. Okay? And because it has like literally every prime number in it, it's pretty obvious that one prime number is able to divide this product right here, right? That's pretty self-evident. So we can say, and we're going to represent a prime number as P, that P divides R. And as we said earlier, because Q is not a prime divisor, or because Q is not a prime, it has a prime divisor. So it's the case that P also divides Q, okay? And then if we think back to like the very first theorem that we wrote out, if it's the case that, you know, if P divides two quantities, then it's also true that P divides the subtraction of the two quantities, like this, right? And what this comes out to, Q minus R, is 1, right? Because Q is the same thing as R, we're just, you know, adding this 1 here. So that means that P divides 1. And in order for P to divide 1, it has to be smaller than 1. And that is a contradiction, because if we remember, P is a prime. And what is the smallest prime? It's 1. And in order for P to divide 1, it has to be smaller than 1. And so P cannot be a prime. So we have found that the negation of R is also true. So R and not R are true. And because this is obviously not possible, we have concluded that the assumption that there are a finite set of prime numbers is false. Okay? Really quite powerful stuff, quite cool. Okay, so hopefully that makes sense. And okay, so the next part, and you can look at this is notated a little better. The next part is, what are good cases to use proof by contradiction? When would we want to use proof by contradiction? As per the first case, the reason for the first case, it's really when we want to show something that's difficult or like doesn't exist, I guess. For example, like an infinite number of numbers, that's hard to quantify, right? Well, if we take the opposite of that, yeah, we're trying to prove something exists. Similarly, we're trying to say square root of 2 is, you know, irrational. So we should keep this in mind when it's kind of like, when it's, I guess the feeling I get from theorems that use proof by contradiction is that they're really far out there, and it would be really hard to tackle this, especially in a finite number of steps. Okay, so let's quickly go over theorem 2.7. The square root of 2 is irrational. So I'm going to switch over to Paint. File new. Okay. So this theorem also relies on a lemma, and that lemma is, if I remember correctly, I believe it's if I'm going to write it down. So we're going to prove, just really quick, that, I switched my color. The square root of 2 is rational. So we're going to try to prove the original statement says that the square root of 2 is irrational, which we know to be true, but we're going to try to prove the opposite of this. And we're going to use a lemma that says if a squared is positive, then a is also positive. Alright, so this is a fact that we can take for granted that we don't have to prove ourselves, right? So we're going to say the square root of 2 is rational, right? So in order for something to be rational, it has to be the case that there are these two, I believe, integers. Yeah, two integers, a and b, such that a divides b, and a and b share no common factors. A, and I'll just write this out in plain English. A and b share no common factors. Okay, and then let's see. So because we're saying that the square root of 2 is rational, then we're saying that the square root of 2 can be represented by a divided by b, right? So we can essentially say that the square root of 2 is equal to a divided by b. Okay, and right now we're just going to square both sides. We're going to say 2 is equal to a squared divided by b squared, and we're just going to throw b squared onto the other side. We're going to say a squared is equal to 2b squared. And as we can see by this right here, this tells us that 2 divides a squared. You know, we've seen this a couple times before. And if it's the case that 2 divides a squared, then 2 also divides a. Okay, so that's actually going to be our statement R. So R is going to be 2 divides A, or sorry, 2 divides B, or I mean A, yeah, geez. Okay. And because 2 divides A, we can actually represent this now as A is equal to 2 times some arbitrary integer value n, right? However, if we plug this back into this equation right here, what we get is that 4n squared is equal to 2b squared, which means that b squared is equal to 2n squared, which means that b squared is divisible by 2, and similarly by this lemma right here, b is divisible by 2. So this is our other r. This is actually not r, because A and B share no common factors. And so we have proven that they in fact do share a common factor, and so this in fact is false. It is false that the square root of 2 is rational. Okay. Oh, geez. Okay. I forgot to switch over. I'll briefly explain what I went through. Hopefully it was sort of clear from my explanation. Actually, it's probably better to look at the really written version. So, I don't know, maybe pull up this video and then pull up a second tab with this video so you can fast forward to the part where I reveal the solution right here, and then just, you know, listen while I go over it. But, sorry. Let's just get through the content. Okay. Section 6, proof by cases. What is proof by cases? This one I sort of had a hard time wrapping my head around because they gave one example, and I don't know if it was really the best, but it kind of is. You're given a couple different situations, and you know that, you know, by some law that at least one of these situations must be true, and by assuming one of them is true, and by, you know, seeing it out to completion, you end up proving the actual proposition you intended to prove. And I know that sounds pretty far out there, but we're going to go over a proof right here. So we're going to say there exists irrational numbers x and y such that x to the y is rational. Okay, so let's switch over to Paint. Save. So x to the y is rational. So we have two irrational numbers, and as per the notes, they are initialized to root 2 and root 2. I mean, this is handy because we just proved that root 2 is in fact irrational. And, you know, our proposition is saying that an irrational number to an irrational number yields a, what does it say? Yields a rational number, right? So we're actually faced with two cases. We can say, well, maybe it's the case that x to the y is irrational, or maybe it's the case that x to the y is rational. So if we say x to the y is rational, I mean, that has no substance, right? Because that's kind of what we are already saying with the proposition that, you know, given two irrational numbers, one irrational number to the other irrational number is rational, so that doesn't really prove anything. But say we assume that x to the y is irrational, right? You know, what happens if we do that? Well, x to the y in this case is root 2 to the root 2, right? So why don't we set, if we're assuming that this number is irrational, why don't we just set, why don't we set y to that number? Set it equal to root 2 to the root 2. And what we're going to do is put it into this and see if this still holds, right? So we're going to say root 2 to the root 2 to the root 2, which is root 2 to the root 2 times root 2, which is root 2 times 2, which is 2, is quite obviously not irrational. It is rational. So by assuming that this case is true, we were able to prove that x to the y, where x and y are irrational numbers, does in fact yield a rational number. Okay, so I hope that illustrates proof by cases a little more concretely. And this is going to be the last one that we prove. There are some exercises that I was going to do, but it's getting sort of late, so I'm just going to talk about the last couple of sections. So, common errors when writing proofs. The first one says to not assume that the claim you're making is true. And let's just take a look at this example. We're going to say our proposition is that -2 equals 2. Well, in this case, the thing we are trying to prove is already assumed to be true, so we can't really pick it apart, it seems like. I mean, that's sort of my interpretation of what that means. I'm sure there'll be examples that I come across when I'm actually doing the problem that will make more sense, but this is obvious even when you're dealing with algebra. Remember to check for zeros, especially divide by zeros. And we'll take a look at this right here. We're going to say that 1 is equal to 2, right? And, the proof that they use is this algebraic expression right here, x squared. And I'll say this. So this will be the last one that I do. So we're assuming that there's two integers, x and y, that are equal to each other, and because they are equal to each other, we can say that x squared plus x times y is equal to x squared plus y squared. And given that, we're just going to factor really quick, and we're going to say x plus y is equal to, what is this? We can use the fact that, oh, actually, we're not going to say plus, we're going to say is minus. Let me just, I'm going to say this, because if we have this, we know that a squared minus b squared is equal to a plus b times a minus b, right? So we're going to say, I'm just going to take this out. I'm just going to say x plus y, x times y, right? And, you know, if we were just looking at these plain unassigned variables, we would think, oh, well, let's just do this. And we see that x is equal to x plus y, and because these numbers are the same, it's really x is equal to 2x, which means that our original claim of 1 equals 2 is true, but where did we go wrong? Well, we went wrong right here, because x and y are equal to each other, right? So x minus y is actually 0. And when we do that, we're proving something that is not true, because, you know, this entire side of the equation and this entire side of the equation would already be 0. So we would be dividing out 0 from 0, and that would just not get us anywhere with actual numbers. Okay, so I don't know why I didn't switch over to... Okay, I mean, hopefully this makes sense. I'll go over it really quickly. So our proof is that 1 is equal to 2. Given that 1 is equal to 2, we can come up with this expression right here. X squared, let's see, x squared minus y squared is the same as x squared minus x times y, because we're assuming x and y are the same. Yeah, so our claim is that 1 is equal to 2, and then we're starting off with the proposition that x is equal to y, and they're in the set of integers, right? And then using some algebraic manipulation, we're going to just factor out the x minus y and divide both sides by that and yield this bogus expression, but it's pretty obvious that x minus y yields the number 0 because x is equal to y. And so really what we would be doing is subtracting or dividing 0 from both sides of the equation. So that's something we should be wary of. Okay, and really quickly, the last tip is to be careful when mixing negative numbers with inequalities. Again, this is just kind of like another algebra thing. We should know to kind of flip the signs when we multiply or divide by negative numbers. So, yep, and then last one, style and substances, or style and substance in proof. I'm just going to read it verbatim. It says, lemmas are like functions in a program. You can abstract away low-level details to prevent yourself from entering a logical ditch that will take time to build your way out of. Yeah, so this is something that I sort of touched on before. The note also says that you can go into those details. Like, if you really want to, you can prove every little thing. For example, if we remember back to one of the older theorems, I believe it was this one, 2.6, we used the lemma that, or sorry, the one I was thinking of was here, was that if a squared is even, then a is even, right? Well, that itself is a proposition that we could prove, but that would sort of require mechanical work that is just simply not necessary if we've already established that is a fact. And, you know, that's just something that you do in programming too as well. If you've made a function, if you tested it thoroughly, you know, there's no point in rewriting the same code twice, right? So that about wraps up note 2 for CS70. I will probably go through some of the exercises in a future video. If not, I'll probably end up doing them on my own. But I'm going to wrap that up right here.